Welcome to your first PyTorch lesson for the MNIST image recognition section. In this video, we will focus on loading and transforming the images. On a new collab notebook, we will start by installing the relevant libraries. The reason we start this project from scratch is because some of the installations in relevant libraries will vary. For instance, not only will we pip3 install Torch, but this time we also install Torch Vision. I'll discuss the Torch Vision package momentarily. For now, I will fast forward this video until the installation is complete. Having completed the installation, we now begin importing the relevant libraries. First, you will import Torch, and from Torch Vision, we will import datasets, as well as transforms. This Torch Vision package is a standard package that contains many types of datasets, most notably the MNIST image dataset that we've spoken of in the last video. And it also consists of transformations that are commonly applied to these images in order to pre-process them before they are fed into a neural network. Two or more packages that we will readily use are matplotlib and numpy, so let's make sure we import those. We import matplotlib.pyplot as plt, as well as numpy as np. Fine then. Let us begin by loading the MNIST dataset onto our project. We set training dataset is equal to datasets.mnist. And in the first argument, we specified the root directory of our data. We will simply specify root is equal to /data such that the dataset is saved in data. And next we set train is equal to true. And we do this to initialize the MNIST training dataset. We will now set download is equal to true as well. And this will simply download MNIST onto the data folder if it's not already there. And the last argument will be transform is equal to, and that's quite an odd parameter. What do we set this equal to? As I've mentioned before, the transform argument simply dictates any image manipulations that you wish to apply on your images. Currently, our MNIST images are 28 by 28 grayscale images, which would imply that each image is a two-dimensional NumPy array, 28 pixels wide and 28 pixels long, each pixel intensity ranging from 0 to 255. We must transform this image from being an array to a tensor. So what we'll do first is we declare a variable transform, and we'll set that equal to transforms.compose. And what compose will do is it will allow us to chain together transformations. The first transformation being transforms.toTensor. This will simply convert our NumPy array in the range of 0 to 255 to a float tensor in the range from 0 to 1, encoded in a tensor shape which characterizes the image's channel height and width. We will also apply the normalized transformation, like so. Transforms.normalize. First 0.5, 0.5, and 0.5. And we do this again, and I'll explain it in just a bit. 0.5, 0.5, and 0.5. What we just did is we normalized the values for each tensor of image size, channel height, and width. In the first set of brackets, we specified the mean that we would like to use to normalize all channels of our tensor image. And in the second set of brackets, we specified the standard deviation. And the reason why we chose 0.5 values for all of them is because ultimately we want to convert our tensor image range to go from 0 to 1 to -1, 1. The way it does this is take, for example, the minimum value of 0 by subtracting the mean and dividing by the standard deviation, both of which are 0.5, it yields -1. Doing the same thing for the maximum value yields a value of 1. hence creating the range from -1 to 1. Why would we want our image values to range from -1 to 1? Well, in essence, normalization helps reduce skewness and distortions within our data, ensuring a more effective learning process once that image data is fed into the neural network. Using this normalization with 0.5 values is one of many normalization schemas. Alright, having finished with our transformations, let us apply them to our MNIST images with transform is equal to transform. And now we will simply output the characteristics of our training dataset by simply calling training dataset. And having downloaded the training data, it provided us with 60,000 training images with the following transformations applied to them. We will further analyze images within this dataset by plotting it. However, to plot the tensor image that we have right now, we must change it back to a NumPy array. So we'll go ahead and do that now. On a new cell, we define a function def image convert, and it will take the tensor as an argument, like so, such that the image is equal to the tensor. And before converting to a NumPy array, first we will clone it, creating a new copy of the tensor, and then we use the familiar detach function in order to call .numpy, ultimately converting our image to a NumPy array. And one should note that the tensor passed in, which we then converted to a NumPy array, has a shape where the first dimension now represents the color channel, the second and third dimensions represent the width and the height of the image in pixels. Ultimately, we know each image from the MNIST dataset is grayscale, corresponding to a single color channel with a width and height of 28 by 28 pixels. Hence, the shape would be 1 by 28 by 28. To plot our image, we require to have a 28 by 28 by 1 shape. So what we do is we set image is equal to image.transpose 1 to 0. We swap axis 0 for axis 1, axis 1 for axis 2, and axis 0 in the end, in order to obtain a shape of 28 by 28 by 1. And having previously normalized the image, now we denormalize the image. The normalization process consists of subtracting the mean and dividing by the standard deviation. So, to denormalize, we would multiply by the standard deviation and add the mean. We can start that by setting the NumPy array image is equal to image times numpy.array 0.5, 0.5, 0.5, reversing the process from up above and adding numpy.array 0.5, 0.5, 0.5. Finally, recall that normalizing previously converted the range of our numbers from the range 0, 1 to -1, 1. To ensure that the range is indeed between 0, 1, we can set image is equal to image.clip 0, 1, applying the clip function to a minimum value of 0 and a maximum value of 1. We can now return the image, return image, and proceed to plotting our MNIST images to obtain a better visual of what we're dealing with. We first start loading our image. We will load our images from what's called a training loader. So we start by defining the training loader. Although this would be your first time seeing a training loader, the training loader is what we use to specify our training batches. Previously, when training our neural network, for every epoch, we performed a single pass through the entire dataset. However, one epoch with 60,000 training images would be too big to feed to the computer all at once, so we divided in smaller batches using our train loader, or training loader, let's call it, to stay consistent. And we set that equal to torch.utils.data loader, and the first argument, data set, will equal the training data, training data set, and we will choose a batch size is equal to 100. With a batch size of 100, it would take roughly 600 iterations to complete one epoch, and at each iteration, it'll update the weights of the neural network, minimizing its error. The batch size really depends on the size of your data, and according to your GPU, how long it takes to process your data. A batch size of 100 is a pretty good number relative to the amount of data that we have. One more thing is to set shuffle is equal to true, so as to shuffle our training data before each epoch. The advantage of this being, as we use gradient descent to update the weight in the direction that decreases the error the most, as it keeps minimizing the error, oftentimes it'll tend to get stuck in a local minimum rather than the absolute minimum. And what you want to do is always ensure the absolute minimum of your loss function to decrease the error as much as possible, thereby maximizing the accuracy of your model. Although when dealing with static training data that's unchanged over all training iterations, gradient descent algorithms will tend to get stuck in these local minima. The solution to this is to shuffle your training data, ensuring that the subset of training data changes with every single iteration. Alright, so we've initialized our training loader. Before making use of it in our training process, we will first use it to load and plot a batch of our images. First, I want to delete this output statement that we have and ensure cleanliness. So let's just rerun that cell. And below, what we will do is wrap train loader, or training loader, I should say, with iter. And what that will do is it creates an object that allows us to go through the iterable, the training loader, one element at a time. So what we're going to do is set data iter is equal to the iterable. And we access it one element at a time by calling next on our data iter. And what that will do is it will grab the first batch of our training data. And that training data, it can be split into images and labels. We next work to plot the images in the batch along with their corresponding labels. We do this with fig is equal to plt.figure, and we set fig size is equal to a tuple of integers, 25 by 4, which simply specifies the width and height of the figure. And now we want to plot 20 MNIST images from our batch, so we loop through a range of 20. For I in numpy.arrange 20. We then use fig.addSubplot. To add a subplot to the current figure, it will have 2 rows and 10 columns per row. Ultimately, 20 images will be plotted. Alright, so the first 3 arguments clearly corresponds to the number of rows, the number of columns, and the third one is the index, ultimately allowing us to describe the position of the subplot within 2 rows, 10 columns per row, to be positioned at the index plus 1. Let's just call this index for clarity, idx, idx. We add the plus 1 since the index, idx, starts at 0. And in its current state, the index must be between 1 and 20, otherwise we get an error. Alright, so now that we've described the position of the subplot being iterated through, we will display an image for every iteration with plt.imshow. And from our images, we access one image within the index idx. And now recall, this gives back a tensor. What we need is a numpy array, so we pass this as an argument to our function imageConvert. We didn't just specify it for nothing. To return an appropriate array that is fed into plt.imshow, and now to each image plotted, we will give it a title, being its corresponding label. So, as addSubplot adds an axis to the figure as part of the subplot arrangement, we can set ax is equal to figure.addSubplot, And now accordingly, for every single ax, we can set title, and we place the label at the current index being iterated through. Labels idx.item. And we'll wrap this inside of brackets, like so. All right, and now before plotting our data, let's add a print statement of our image shape. We will do so right after transpose print image dot shape. And running both cells, you can clearly see that each image has a shape of 28 by 28 with a single color channel, obviously since the images are grayscale. And down under, we see our grid of images, each image associated with a label. Before finishing off this lesson, let's just get rid of these tick marks over here, these horizontal and vertical tick marks, and we can do this by going over here and setting x ticks is equal to an empty list, and y ticks is equal to an empty list, rerunning the following. All right, all the images and their appropriate labels. We will now use these previously labeled images to train our neural network to classify new test images that it's never seen before. We start building our neural network in the next lesson.